Yeah. Okay. So let's just look at what we're going to go through today. Here it is. I can hear it. Okay. So yeah, I thought we. No, that's wrong. This should be AXI Slave. So we're going to create an AXI Slave IP core, and what that basically means is our IP core that's in hardware can't initiate any memory transfers. So all the sending data and getting data from the device is done by the processing system. Okay? The hardware isn't going, I want that memory location from the processing system. Okay. All right. So we're just going to use the basic Vivado wizard to generate it, and we're going to set the number of registers. So yeah, you'll see. So basically you can have a number of registers in your IP core that are addressable, but I'll get onto that. We're going to then get this IP core and put it into a complete Zynq system. So we're going to get the Zynq processing system and hook up the AXI connections to the IP core that we've just generated. Okay, and then I'll talk a bit more about this address space stuff, which I think most of you know about. But okay, then we're going to customize the IP core. So we're going to dig down into the VHDL code and change it from just being simple registers to having adder functionality. And then we're going to do some stuff with rebuilding the system and managing the, getting Vivado to update the IP core numbers. Yeah, so the version numbers. Okay. Then this is the interesting part down here. So once we've got our base system done, we're going to be, I'll talk about how you access it in a bare metal example, but I won't actually do the bare metal example. Oh, sorry, this bit here. I'm going to, how to program the FPGA from within embedded Linux using xdevconfig. And then I'm going to talk about how to use /dev/mem to get a virtual address for the FPGA IP core. And then you can use that virtual address in very much the same ways that you would in the bare metal example to manipulate the IP core. And it's fairly straightforward. Okay. So let's just create our simple adder. Okay. So I'm going to use the Boxer machines, and I'm going to SSH in with X forwarding. So this means that you can get graphical user display over SSH. So SSH, to do this, we do -x-c. I don't worry too much about taking notes or anything like that, because it's all recorded, and I'll give you guys the recording. So I'm going to connect to Boxer 0. Okay, now I have, if you go to the highest level directory, you'll see this folder here, network scratch, which is available to all users in the group. So if we go into network scratch, and then Shane tutorials, and then AXI Light S tutorial, you can access all the files I'm going to be using from inside there. Okay, so we'll make a Vivado IP core. Okay. Wait, I should, yeah, let's give that a different name. Okay. Simple adder IP. Okay, so I'll just launch Vivado now. You've been using Vivado as well, right? No, plan ahead. Okay, so there's many different ways to actually go about getting to this wizard. This probably isn't the best way. Andrea has a way where you create a repository where you can manage your IP cores a bit better. But I'm just going to do it the way I know how for now. So I'm going to create a new project. And I'm just going to call this junk project. And we're going to skip through these. So we don't need to add any files. We'll do that all later. Don't need to add any constraints. And we're going to select the board. So in this case, I'm going to try and connect to the Z board that's on Yoshi's desk. So I'm going to select this one. Although I don't think it makes a difference for you with the ZC702 because they're both using the same devices with the same layout. So it should be okay if you select this one or this one. Okay. Okay, so this will generate project. All right. Okay, let's actually make this. It looks a bit cramped on the screen. Okay, so now to create a new AXI peripheral and to get the boilerplate code. So what I mean by boilerplate code is this is the code that Zynq gives you when you want an AXI IP. So it's just like their base level project, AXI project. Okay. We go to, oh yeah, it messes up when it's full screen actually, that's why I didn't. Okay, bear with me. Tools, create and package IP. Okay, so here we can actually get our current project and package it into an IP core, or we can create a new AXI full peripheral. So I'm going to select create a new AXI peripheral because we're going to make a simple adder. I'm actually going to put it directory above. Okay, so now we can give our vendor name. The library, I don't know, what library should we have it in? User, sure. And we'll call it simple adder example, or just simple adder, let's just leave it at that. Okay. Simple adder, and a simple, which what?
The version, keep the version in the display name.
Oh yeah, okay. No, that's a good point.
Sorry, display name.
Just in display name? Yeah. Okay. Oh, sorry. Go away, Josh. Okay, so here we can add the number of AXI ports that we want, or AXI interfaces. So the first one it gives you by default is just the slave one. And like I said, slave interfaces can only be written to or read from the processing system. So the processing system, the Linux environment and software, has to initiate the memory calls and reads and writes to. If you had it set up as, no, not here, as a master, then this could actually pull data from different memory locations. To use this from VHDL is a little bit more complicated, but it's very possible. Takes a bit more hacking, basically. Okay, and you can also add more, and then you can have them as streaming interfaces or full. This allows like burst transfers if you're doing high throughput data. But since we're only, in this example, going to be doing single numbers, a light interface is fine. So typically if you were doing something like video or yeah, video is a good example, then you'd use a streaming interface. Okay, but we'll stick to light, and actually we don't need that one, so single one. And then the number of registers. So this is actually the number of addressable parts of our IP core. Is there a whiteboard marker? Can I borrow the whiteboard? Thank you. So if this is our memory space, okay, we go from 0x00000000 to 0x3ffff. So this is the memory space of the processing system. So inside here, let's say if you've got Linux, part of this will be reserved for the kernel. And then programs can use this memory space, right? And basically how you would access a memory location here if you didn't worry about Linux, let's say 0x200000000, is you would actually create a pointer to that location, right, and then dereference it. Do you know much C programming? Yeah, okay. So let's say we wanted to set this memory location to that value, then we would just dereference the pointer, sorry, I'm in the way, and we could set it in here. In a very similar fashion, for what we're doing here is the devices exist in this memory region. So everything from 0x4 and upwards is actually an AXI device. Sorry, an AXI device living in the programmable logic. Okay? Or further up again, then we have actual I/O devices that are hardwired. So when we say the number of registers here, our device will be plopped somewhere in this memory space. So let's say 0x4C000000, and the extra registers will then be the increments of this address. Okay, so let's say we wanted to write to the third address, then since each address is 32 bits wide, so that's 0x04 in hex, then we would add 3 times 0x04 to this address to access that location. Does that make sense? Have I lost you guys? So this is totally configurable for you. So let's say, in our case, we probably only need 3, right? Because if we're doing C equals A plus B, then we'd only need a register for the output, and a register for both the inputs. So I'm going to change that down to 3. Oh, you can't. The lowest you can go is 4, but we'll just waste 1, right? I wonder why that is. Do you have any ideas why 4 is the minimum? Okay. Right. So you also have the option to generate some drivers and things like that, and they can be quite useful especially for bare metal stuff. But when you're using them in Linux, you'd have to do a bit of hacking. But it's the same sort of hacking that we're going to have to do anyhow. But I'm going to do this from scratch. So, okay. And then you can open it and add it to an editing session. So this allows us to actually edit the VHDL code that comes out. Finish and we wait. Okay. All right, and I think that's it. So this is the VHDL code that comes out. Now, don't worry too much. You've had some experience with VHDL already, right now? Just some. Yoshi, you haven't done any before? Okay, don't worry too much about it. VHDL is pretty. It's not too difficult, but there's a lot of little fiddly rules that you need to know. So I wouldn't worry about not understanding this code for now. But okay, so we've created our IP and we've packaged it. So then if we go here, I think we might package. Oh yeah, okay, I didn't need to do that. Right, okay, so I'm going to close this for now. Oh. And I'm going to create our Zynq system. So this will be the system that will have our 2 ARM cores in the processing system. Which will be running Linux. And it'll tell Vivado how we want this connected to the IP core that we just made, so our simple adder. So as you can probably tell by now, to do this sort of stuff, you need an awful lot of Vivado projects. It seems to, yeah. So the Zynq system. Okay. I'll just okay, so I'm going to create a new project, and we're going to call this Zynq system, just because it's got our okay, and again we can skip through all these, and we select the same device. Okay. Now the first thing that we need to do is create a block design, which is here. And this basically describes this thing. So we get blocks for all of our IP cores that we want to connect up to our system, and we get blocks for the Zynq processing system, and we click them all together. Okay, so we're going to create that. You can call it whatever you want. I'm going to call this, yeah, design 1 is fine. Okay, oh, let's open here. Okay, I'm just going to close that for now. Okay, so at the moment it's empty. And the first thing that I'm going to add is the Zynq processing system. So this is this part, the ARM cores and the I/O. So we load that in here. Okay. And the way it instantiates it isn't quite correct, because based on the board presets, so how the Z board is configured and how the Zynq devices, the ZC702 is configured, this DDR needs to be hooked up to some external input-output ports to actually connect to memory on the device. But it can automatically do this by going to run block automation. So if we run block automation on the processing system, yeah, you'll see it'll connect up the I/O and the memory, and it will apply the board presets of whatever board you've set up. Okay. You can see that it's done that. Now the next thing that we want to add is our IP core. And to do that, we actually need to go to the IP catalog to make it available. So inside here, this is basically a collection of all the IP that we can use in our devices. So there's like FIFOs, yeah, sorts of things like adders and subtractors, Cordic engines, all those sorts of things, right? And we want our IP to be available in this list. So we go to IP settings, and we add a repository. And the repository is basically the folder where we created that IP project. Okay, so in this case, it is simple adder score 1. Okay, and you can see it's there. So this is the one that we just made, right? Okay. So we're going to apply that, and then we're going to go back to our block diagram, and we're going to add the IP. So, oh, yeah, this thing never likes exporting. Okay. So simple adder, there it is. Okay. Okay. So you can see this has a slave AXI port, and then just a clock and a reset. So this is where all your registers will live. So those 4 registers that we set, they will be accessible through this AXI connection. So whenever Vivado detects that there's an open-ended AXI connection, it'll give you this run connection automation wizard. So if you run that, you'll see that this one's available, and it highlights it. And if we click it, it'll find a corresponding master that it can connect to. If there's no master available, the connection automation won't be there. And the master that it's going to is actually in the processing system here. just for future reference, in case you do want to make masters inside the programmable logic that want to access the processing system's memory space, you can expose slave AXI ports in the processing system. And to do that, you open up the processing system like that, and if you go down here to the slave ports, you can actually enable them. And then once you do that, you should see that, yep, there is an extra slave port over here. But for now, we don't need to worry about that because the processing system is in control. So it's the only master that we want. So I'm just going to remove that. How are we doing for time? Okay. Okay. So we'll run the connection automation to connect our adder. And yeah, we'll connect it to the AXI master of the processing system. And then it takes longer than it should to think about this, probably. It doesn't seem like that hard a thing to do. This is particularly slow. Okay, so it connects it up, and it does it through quite a convoluted way of various interconnects, and it's got a reset system. I think it also hooks up your circuit to the AXI clock, which just connects to the AXI clock of the Zynq device. You can fiddle with this and have it off different clocks if you want it to run at different frequencies, but it's slightly more complicated, not much, but okay. So that's our system. This is we've got our adder hooked up to our processing system. Now, how do we actually access this thing? So if we go to the address editor, we can see that the address for a simple adder has been dumped in this region, so outside the RAM of the processing system and into the I/O memory space. So it's got the address. Maybe we should write that down because we're going to need it for later. 0x4 3C00000. And we had 4 registers, right? So register 1 will be here at the base address. Register 2 will be at 0x43C00004. And then 3 will be at 0. Every time. 0x43C00008. Right, so we won't worry about the 4th one. So let's pick arbitrarily. Let's make register, actually in the device they're labeled, they go from 0, 1, 2. Okay, so let's have this as C, this as A, and this as B, right? So this is our result, and then these are our 2 inputs. Sound good? Yeah. Okay. All right. So what we want to do next is actually change the simple adder so that it acts, right? So let's close this for now. We need to save. So if we go into our simple adder project and we go into the HDL directory, then we'll see that we've got these 2 files. So this one is the top level file, so simple adder version 1.vhd, and this basically just exposes all the ports. And if you had more of these AXI devices, it would say how they all connected together. As this one is the one that we are interested in. So I'm going to use Vim to actually edit. Whoops. Oh wow, this thing is okay. Right. Oh, what am I doing? Okay. To actually edit this file. Okay. So these are all the standard AXI interconnect things. So you've got things like the write address, and when the write address coming in is valid, and all these various handshaking things. So the write data. Don't worry about this too much. All you need to know is that when the address comes in, this stuff magically knows which register to dump it into. And the registers that I'm talking about, I went to the wrong one. Whoops. Oh, what am I doing wrong? 0. There we go. Yeah, so these are all the, and it's actually pretty well commented. So it will tell you, write response, this signal indicates the status of the write transaction, and all the various plus handshaking and transactions stuff like that. Sorry, that's incredibly hard to read, the comments. But yeah, okay, so like that one there. So actually I found the best way for doing AXI stuff in VHDL with the Zynq tools is not to worry too much about the official documentation. Look at the comments in the code that comes out. Okay. So here are our registers, right? So we have register 0, then register 1, and register 2. So in our case, this will be C, the result that's coming out. This will be register 1, and this will be register 2. Okay, so at the moment, anything that comes from the processing system into our IP core can read or write these registers. But what we want is we want the C register to be written to by our IP core with the result of these two additions. Okay, sorry, have I lost you guys, or is it? No, it's okay. Okay, but don't worry too much about hacking about with the VHDL code. So I'll just do this quickly. So for the, this is the write process, I think. Yeah, so we don't want, because in VHDL there's these funny rules that only one process can write to a register at a time. So we'll just get rid of all the writes to SLV reg 0. Okay. And we're just going to edit it so that we have SLV reg 0 is SLV reg 1 plus SLV reg 2. Okay, and that's it. Simple. So, yeah. All right. Okay, so now if we open up Vivado again, oh, whoops. Okay, so sometimes X forwarding fails, and that just means that I no, come on. Nope. I just need to log back in again. What am I doing? Vivado again. Okay, and I'm going to open Edit Simple Adder, which is the project that I was using for editing the IP core. Okay, can't do that. So if we do Zynq project. And I'm going to go to the IP catalog and find our simple adder IP, and then edit an IP packager. And this just creates a temporary project again for doing that. Again, don't worry about following all of these steps because it's all recorded and you can just follow through. Okay, and if we just check the code, just to make sure that it did actually update. Yep, there we go. We've got our slave registers. Okay. Now we can just try quickly running a synthesis just to see if, just to make sure that it is correct and that my VHDL code will work. Are you guys getting used to watching what comes up on the screen yet, or no? I think it's okay. I think, oh, yep, okay. So that's fine. We know that our, at least it synthesizes. It doesn't mean it's correct, but it synthesizes, so very far from correct. So now we can open up our Zynq system project again. Oh no, sorry, we can't do that. First thing we need to do is actually package our IP again. Where did that go?
Nowadays, simulation are analysis.
Oh, right. Yes, thank you. Yeah. Okay. Thanks, Andrea. Okay, so I'm going to actually increase the version number. Because if you don't do this, Vivado doesn't always detect that the IP core has changed and update your system. Okay, so that's that. Now once we've repackaged, we can open our Zynq system. What am I doing? Whoops. Here. Yep. Okay, so it's detecting that it's changed. So if you now go to Tools, Report IP status, then we can see that it says that please review the change of this. And we can actually go to Upgrade Selected. And now this will upgrade our IP with the new version that we just made.
How does it know it's a new version?
So that's why I changed that version number. So now if we actually go to, hang on, I'll show you. If we go to our IP catalog, IP settings, here you can see it's gone from being version 1.00 to 1.01. So when I repackaged it, I just added the extra 1 on, so it knew that something had changed.
And it knows to choose the higher number?
Yeah, it always kind of wants you to update. I mean, you don't have to upgrade, but yeah. There's probably a nicer way of doing it, but it's kind of hard to find a way that works. With Vivado HLS, the updates are more automatic. You don't need to create a new version number. It seems to just work when you change them. But, yeah. Okay, so now that we've got our system, we can actually build it. So in order to build it, we actually need to create a top-level entity, which just means you just go to your design and go generate HDL wrapper, and this just exposes all the output ports for things like the processing system, stuff like that. And you may as well leave Vivado manage that, unless you're doing some crazy hacking. Okay, so that's that. Now we can have a cup of tea, a few minutes, and actually generate the bit stream. And hopefully it'll go through the synthesis and the implementation okay, and a bit stream will come out the other end, which is what we can use to program the FPGA. So if I do generate bit stream, yeah, okay, so wait around for a few minutes. There we go. Okay, so if we go into our IP core, right? Okay, so vim simple adder. Okay, so inside here, oh, okay, I'll just show you this quickly and then we'll go back to that. So inside here, we have our slave registers, right? So what you can actually do is you can create your own VHDL components separately and then import them into this project. So you can like have, I don't know, house module, and then you can have a port, and then the port listing for all the ports into your module, and you can send an SLV reg 0, and that sort of thing. Does that make sense? So it's kind of like an include in C. So you. So this isn't actually for the software. This is what describes the hardware. So this is like using Vivado HLS. So the difference between using this and Vivado HLS is you can get much more lower level optimization. It's much more difficult to program in this, but you can get much better results. Yeah. So I can show you how to do this another time. Sorry, I should actually probably. I think it would be, yeah. So then you'd have a signal in here, like, yeah, so sorry, it connects this. So let's say you have a switch that turns something on and off in your VHDL module that you've created somewhere else. So you'll have switch 1, and then you can have that connected to SLV reg 0, and then, so this syntax is probably wrong. I'd need to look it up, but, and so on. So you can actually get your AXI signals, which are connected to the memory space, and hook them into your own VHDL code. Make sense? Or? Okay. So you can see this sort of as, you know, so you have your IP core, or you have your code that does what you want, right? So let's say you've got your FPGA circuit, and you've got this block here, and then this block here, and you want to turn this off occasionally, and sometimes turn this off, right? And you have some signals as inputs into your block to either turn these on or off, right? Okay. So what we can do is we can create this as sort of like its own VHDL file, and then bring that inside our IP core, that we make through Vivado. And then this has all its AXI connections, but then it's got the SLV, the slave registers that we can use. Okay. So that'll be slave register 0, slave register 1. Okay? And these all get connected up to this in various ways. But we can just map these into that. And then this whole IP core can go into your system and connect to your 2 ARM cores in the bigger project. So this would be the IP and your VHDL inside, your VHDL project inside. Does that make sense? Okay, so our bit stream has now generated, and as you can see from the implementation, it is tiny. Yeah, it doesn't take up much logic resources at all. So I'm going to export this bit stream. Export bitstream file, and I'm going to go into this folder that I made earlier called output bitstream, and let's just call it simple adder system. Okay. All right. Now, okay. So now we can close Vivado and forget about it. I'm going to open up a new tab, which I'll use in a minute. And the first thing I'm going to do is, oh, whoops. Go into this folder where I've got this script called promgem script. And what this does is it prepares the bit stream for programming within Linux. So we can actually reconfigure the FPGA device from inside our embedded Linux running on the dual ARM cores. But in order to do that, we need to actually reverse the bit stream. So you just have to put it through this script. And the script is very simple. It just calls this program with some settings. Yeah. So scripts, simple adder, and there we go. Okay, it's generated this extra file, which we're interested, .bit.bin. So we can now use this to reconfigure the device. So I'm going to use, since we can't connect to the Z board, I'm going to use the ZC702 board on my desk, which has got the name Europa. So I'm actually SSHing into the Zynq device now. Okay. And I'm just going to make a directory called adder example. Okay. And what I'm going to do is I'm going to SCP, so this is just transferring over SSH, the simple adder system.bit.bin to the Zynq device. And what was that folder called? It's called adder example. I spelled it wrong. Okay, there we go. It's transferred across. Now inside here, there we go. We can see it. So to reconfigure the device with our adder system, I'm just going to do cat and then simple adder into this device file here, dev xdev-config. So this is the configuration port for the FPGA, and Xilinx provides some drivers for doing this. Okay. So from that, the device is now configured very fast. Okay. Now what we need to do is actually get software to interface with it. So I'm going to create now a simple C file, which I'll call sample interface, maybe adder interface. C, okay. Oh, whoops. Okay, and I'm going to define just our base address, which is here. which is its location in memory here. So that's 0x4 3 C 0 0 0 0 0. Okay, and I'm going to grab some files that I had earlier. Vmap function. Okay, so just grab. I'll just copy this for a moment. We probably don't need all these header files, but I'll just include them just in case. And then I'm going to have an extra function, which I'll explain now. Okay. So what this function does is it actually gets a virtual address for this physical address. So in Linux, if you try to actually directly access this location, you get a kernel panic. The kernel would say, you're accessing memory that's out of bounds, you need a driver. You are only allowed to access this memory space, and only if I've allocated you a virtual address for it. So that's what this does. It actually opens this device file called dev/mem and gets this memory space is accessible through that file there. And it gets us a pointer to a virtual address to this location in that file. So that file there, the device file, can see the entire memory space of the system. Okay. So this is a very hacky driver, and you need to be root in order to run it. If you want to make a proper driver, that's slightly more complicated, and I can explain that to you if you want. The advantages of using a proper driver is it's safer. So let's say you have a system with multiple users all trying to access the same device. Then you can put things like locks on to make sure only one person can access it at the same time, and things like that. Okay, make sense? Okay. So we've got this function that gets a virtual address for us. And we've got our device's base address. So the first thing we're going to do is get a virtual address for our base address here. Okay, so I'm going to have an integer pointer called, this one is going to be output C, because this actually exists at address 0, register 0, right? And this is equal to, we're going to use vmap, a virtual address function, to return. So a virtual address is just a way of, so they're used for a number of things. They're used to make programs look like they have unlimited memory. So the operating system gives it a virtual address, and then it goes through various mechanisms to convert that into a physical address, such as pages and things like that, so that they can get swapped out to slower memory locations. But it also stops other applications accessing each other's memory addresses. So it's quite a complicated thing. And I think you learn about that in second year computer architecture, you know? Or, yeah. So I think the more, as you go further on in computer architecture courses, you learn more about this virtual address thing. But basically it's like a fake address, and the physical memory gets managed by the operating system. That was a really crap explanation, but yeah. Do you have a better way of explaining it, Andrea? Or no? Okay. All right, so, yeah. Sort of like, if you have your physical addresses here, right? And you have a bunch of them, and then you've got like a slower memory space down here, and you've got like a bunch more addresses. The operating system, the application appears like it's got infinite memory, but what in actual fact is happening is if it requests this address and there's something already in the physical location of that, it will swap it out and grab the right one for that application. Sorry, that probably confused you even more. Yeah, okay. Right, so we get the virtual address for the output, and now we can do the same thing for input A. Sorry, I'll go down a bit more. Give it low down. Okay. Okay, so we actually, yeah, let's do this a different way. So we'll call this device-based virtual address, okay? And then we've got a virtual address for this region, and we actually grab virtual addresses for, I think in this case, 4 kilobytes afterwards, which is unnecessary. And it's set up here, so this is the map size. So we don't need to get a virtual address for each of our registers, just for the base, and then we should have addresses incrementing after that. Should map to addresses here. Okay, so input A is equal to base address plus 1. Because it's an integer pointer, it's incrementing by the size of an integer, which is 32 bytes, so we'll increment by 4. Yeah, okay. And then for int star input B, we have dev base address plus 2. Okay. Right. So hopefully this should work. Oh yeah, okay, so then we can just have, we don't have C anymore, int star C equals dev, oh sorry, this should be v address, virtual address, dev base virtual address. Okay. No, because this is actually at location 0. See, sorry. Yeah. I didn't need to do this. I could have just used dev base this, but I thought it would make it a bit clearer. Okay, so what should we set A to be? Start off with any value. 10? Okay. So to do that, we need to dereference this pointer. So input A is equal to 10. Okay, and then B, what should we set that to be? And then 30. Okay. Okay, and we can try printing out the answer. Let's call this output C, just to be clear. Output C. Okay. All right, and then I'm going to use GCC to compile it. Okay. Where did it complain about that? Undefined reference vmap. Oh, right. Sorry. I meant to use the function to get the virtual address here. My bad. The answer is 40. Should we try changing the values? Okay, what should we change it to? 20. So 80. Okay, so this should be 100. Yep. Cool. All right. So very simple example, but
Maximum number we can use for the input is limited by the Verilog block multiplier.
sorry?
I mean, the maximum number we can use here is limited by what we declare in the when we do the IP. When we make the IP.
So it'll be limited to 32 bits. Is that what you mean? So these are all 32 bits. But you could use this for, let's say you could have one register for the high number of bits and one for the low number of bits. And you can get a much bigger number if you wanted. But then you'd have to obviously do 2 reads and split your number in half. Yeah? Is that what you meant? Or yeah? Okay.
Why does it go up by 4?
Let's go by 4 because it's in bytes. So because each of these registers is 32 bits long, that's 4 bytes. So this goes up 4. But if you notice in the code, I only add 1 instead of adding 4 to go up. And that's because this is an integer pointer. So the compiler knows that the size of an integer is 4 bytes, so it automatically does that when you add by 1. So in actual fact, what it's doing is 1 times size of int.